First Spin. Welcome to First Spin, a show where I learn about the Parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts.
It's expert musical chairs. Welcome back, Roy.
Expert musical
Thank you.
chairs.
And if you cough this week, I will personally beat you with a rubber hose. I might tired of editing out your coughs, man.
Addie, I think you need to change that intro now after 30-something episodes.
You
have prior programming experience now at this stage in the...
Doesn't count. Well, I mean, like C or Java or C++ or C Sharp or like D or E.
But you have prior spin programming experience now.
I guess
you probably program more than some of the people listening.
Is that scary?
Yeah,
you guys should get programming. I shouldn't. You're
like a hardcore elite hacker now.
No, not really. No,
not even a little.
No. I'm glad. I'm still happy when an LED blinks on. Although I haven't made LEDs go on.
It's cool when LEDs blink too.
It's true. Yeah, I have to get these modules wireless, and I've been saying that for the past 2 weeks.
Using XPs to communicate from one board to another and control the module.
Yep. But actually, the first one was a bit difficult to do, and that was just the ping sensor. So I'm not even really sure how I'm going to do the other stuff that requires like complex objects and whatnot. I don't know. We'll see. We'll figure it out.
I think you're probably just making it harder than it really is.
Probably. The last time I made it a little harder than...
You're really good at that.
I know. What can I say? But today we are going to talk about mechanical gyrations. And by gyrations...
Not the dirty kind.
Gyrations like hula hooping.
It's not cyborg porn or anything like that?
No, this is a children's show. Hula hooping.
Gyroscope modules.
We're going to talk about the Parallax Gyroscope module L3G4200D. As if that wasn't complex enough.
Which is 3-axis.
Right, correct. X, Y, and Z. Oh, did I leave that out?
Well, no, we both did because we said gyroscope module, and then you did the L3G4200D, and there was 3-axis in the middle.
Oh, I see.
Anyway.
Whoops. Well.
No whoops.
Yes. So I think we talked about this, I don't know, at the way beginning of us starting to talk about modules. I didn't really remember what we talked about, so we're just going to...
Well, I seem to recall you were starting with that one, and we kind of said, that one's kind of hard to be the first one you work with, so you should go back and do something simpler.
I was explaining.
And you're like, okay. That's your whole trying to make it harder than it is thing.
Right, starting with the hardest module first and then working backwards. That darn PIR sensor. Wait a minute. It only has 3 pins. Yeah. Anyway, okay, so gyroscope module. This thing, and we're again going to learn.parallax.com, is a modular angular rate sensor that tracks motion in 3 axes. There's 3 measurement scales with rates up to 2,000 degrees per second, and there's even a built-in temperature sensor. Now, this temperature sensor, is that the temperature of the chip?
Yeah, well, the MEMS technology that they build these modules out of has characteristics that change slightly with temperature.
Okay.
And so they usually put temperature sensors in these kinds of modules so that you can detect the temperature of the chip and adjust your math to make the readings more accurate.
Okay. Gotcha.
It's not something you need to worry about for basic usage, but if you want to have a really accurate gyroscope, then you need to factor in the temperature appropriately to get your readings to be very accurate. It's not the kind of temperature sensor you could use to just tell you the ambient temperature in the room.
Okay.
So much. I mean, it'll be close. It'll be related, but it's really more about the temperature of the MEMS, the inside the chip.
Okay, gotcha.
So that you get the readings correct.
Okay. And this module provides three separate data values for yaw, pitch, and roll. So what exactly is yaw, pitch, and roll?
Well, those are airplane terminology things for X, Y, and Z.
Okay.
Not in that order though.
Right.
It depends. Like some people rearrange the axes around differently, but in airplane terms, your yaw, pitch, and roll are relative to an airplane as it's going through the air. So pitch is if you're moving the nose up and down to change to dive or climb.
Take off, yeah.
Right. So that's adjusting the pitch.
Okay.
And then roll is if you were to do a barrel roll, right?
And so that's
rotating the plane around its center in the direction it's flying, right?
And then yaw axis is the propeller spins.
So like
right. And then yaw is rotating horizontally, so like turning left or turning right. So if you were to use the rudder on the tail to go to turn the plane and head toward, bank to the right or bank to the left.
Okay. So when a canoe capsizes, that's the canoe rolling.
Yeah.
Okay. Got it.
Right. Yeah. And so what this sensor does, it allows you to measure the rate of rotation in that direction, in each of those three directions.
Okay.
So as you are rotating, like if you grab the board that it's on and turn it with your hand, while it's moving, you'll get a reading.
Okay.
As soon as you stop moving, it stops doing any kind of reading because it's the rate of change. It's not how much it changed.
So why would it be more useful to give rate of change as opposed to how much it changed?
Well, it depends on, the how much it changed is actually a more difficult thing to do as an absolute thing. That's more in the realm of an accelerometer or a compass. But even those have issues because an accelerometer, you're measuring gravity all the time. And then if you turn it, you can't assume that it's just a rotation because it might also be moving. But for a gyroscope, it's the rate of change. So like the thing that they use it for is to help with stabilization. That was like what they were invented for, is stabilizing aircraft and ships. Right. So if the gyroscope detects a rotation, because you're rotating on one, like if you're on a ship and it starts to roll one way, what the gyroscope readings will cause to happen is some mechanism that they put onto the ship to counter that roll to stabilize it back the other way.
And it'll do it based on rate.
Yeah, well, it's just an immediate reaction to the gyroscope says we're rotating this way by this many degrees per second, so we need to turn on the buoyancy thing on this side to counter that.
So that
a simple example would be a feedback loop between a gyroscope and, say, a counterweight that can be pushed side to side.
Right.
So if your gyroscope feels that it's rotating around its, one of its axis to the left, it just rotates its weight a little bit more to the opposite direction until it rights itself, and then it keeps adjusting until it's standing perfectly upright.
But then that means the gyroscope has to work with something else, because if the if you measure the gyroscope and, like you said, like it measures the rate of change. So if it stops changing and it's at a tilt, like the Leaning Tower of Pisa, well, the change is 0. So unless...
Right. So, the idea, though, is that it's more for the immediate reaction to know, like, okay, I'm turning this way, so I better react back the other way. Because, like, if you're in an airplane and you want to bank to turn, you don't want it to level off back immediately.
Right.
You want to stay turned to the side. So you have your pilot, has his yoke that he pushes to the side or turns, depending on the kind of aircraft. And, he wants to stay stable but tilted sideways. Right. So if you want something that automatically rights the plane back to level or whatever aircraft, then you need to have something in combination with the gyroscope, like an accelerometer.
Okay. Which I don't think we've done yet, right?
No, I don't. I'm not sure if we have or not.
Okay.
I don't think we have.
I don't think we have, because I don't even know if we have one. So.
Well, we did the compass module, right?
Yeah.
So
that was easy.
a compass module is sort of a specialized version of a general purpose magnetometer.
Mm-hmm.
And you could use a magnetometer to help you with righting yourself if you are in a known magnetic field, which, if you're on Earth, you have the magnetic field of the Earth. Right. And if you can isolate that, then you could align yourself with that. It tends to be a combination for most devices. Like if you see some of these quadcopters that will automatically level themselves,
right?
They tend to use a combination of accelerometer, gyroscope, and magnetometer.
Okay.
Or compass module.
Yeah.
So that they can read in the data and fuse it all together with a bunch of math to tell when they're turning, but also to correct themselves back to upright.
Sounds like Kalman filters.
They use that sometimes. There's a couple other methods that are common also.
Let's not talk about Kalman
filters.
That's
probably beyond the scope of this show at this point.
Absolutely.
But for gyroscopes, the main thing that you can actually build a quadcopter that will fly relatively easily with just a gyroscope, because the gyroscope can be used to at least keep the craft stable.
Mm-hmm.
It won't automatically right it, but it will help keep it stable at whatever setting you put it at.
Okay.
And that happens to be how the default Elevate works, which I have one of those from Parallax.
Mm-hmm.
It just has a gyroscope module on the main board that comes with it. And when you fly it, when you turn the stick to the side a little bit, it tilts sideways and it stays tilted until you turn the stick back the other way to level it off.
Okay.
So it's a little bit tricky to fly if you're not familiar with that kind of flight control, but it's a lot easier than if it didn't have the gyroscope at all, because then you'd have to control the motors manually and level everything off yourself, and that's really difficult.
Yeah,
to get it to be stable.
Right. So it's mostly for flying objects, not necessarily for even boats, I guess, but not necessarily like an all-terrain vehicle.
They use those in little balancing robots.
Well, I was going to say they use them. They use them on the two-wheeled balancing robots, or even the single ball balancing robots. The other place that they're really commonly used in the mass consumer market is in your cell phones. They use them to detect when you tilt the phone, rotate it to the side or not, and they usually have them in combination with accelerometers to allow the phone to detect which way it's being held. And it allows it to do things like the sky map applications, where you can move the phone around and aim it at the sky, and it'll show you the stars that are in that direction.
So is it like a constant comparison between the last known rate and the current known rate?
Well, no, it's just this particular module is just what's the current rate. That's all it gives you.
In application.
Oh yeah, in software you keep track of the rates. I mean, you can. It depends on what you're trying to do with it.
We talked about this with the accelerometer.
Well, we haven't gone through it yet.
When you did the accelerometer?
We didn't do the accelerometer.
We haven't done a show on it yet? I know you've played with it already, though. No?
No.
Time traveling Toymakers again on here.
Talking about the future that hasn't happened yet. No, I don't think we have one.
We did. We've talked about it with other things, though, is that, I mean, depending on what you're trying to do, you might keep track of the previous rates and factor it in with the new rates. The main thing that you'll end up with that is, you'll accumulate error as you keep track of the settings, because you're going to have a little bit of drift and whatnot.
Sure.
And the precision of how quickly you sample it and how quickly it samples. Because it has a fixed rate at which it can give you feedback data.
Okay.
So you're gonna, it is useful. Like, you can actually keeping track of the rate of change, you can kind of keep track of where the thing is at as far as its current orientation, but it will eventually get off and be out of sync.
Okay.
But for some basic operations, it might be enough, and some applications just do that. But the reading it and reacting is a common thing. Like the quadcopter is just when you get a roll reading that says, hey, it's rolling to the left, rolling around towards the left, you can adjust the motors to compensate for that and correct it back the other way.
Okay.
And then you can also read and say, oh yeah, it's correcting itself back the other way.
Okay.
Because you know from reading it that it is.
Right.
And then you're constantly doing all these adjustments in all directions, and that's what keeps it stable. Is that the processor is constantly adjusting all the motors based on the readings from the accelerometer or from the gyroscope.
Gotcha. So that's got to be actually in a pretty fast system. So this module is actually really small. It's like nearly 3/4 of an inch by 3/4 of an inch, give or take.
Something.
Well, technically 4/5, but that's because I'm actually reading the numbers. And we've got a whole bunch of pins, more so than other modules. But let's see. We have ground, VN, and the power requirements are 2.7 to 6.5 volts.
Yeah, so it'll work with propeller or basic Stamper Arduino, any of those.
Right. And this is an I2C module, so it's got the serial clock and the serial data line.
It can also do SPI.
Okay.
Which is why it has the CS and the SDO pins.
So SDO is serial data out?
Right. So like with the compass module we talked about a couple weeks ago, and I think also the altimeter, which was last week.
Yeah.
These modules do both I2C and SPI, and they're sharing some of the pins. So when you do I2C, you have the SCL and SDA, which are clock and data. But then when you do SPI, the data is split to input and output. So SDA becomes input and SDO is output.
Okay.
And then the CS is for chip select. So it's selecting that device to say you should respond to the serial signals.
So is it kind of like the address for the chip?
It's kind of. I mean, when the CS pin is active, then that chip will be reacting to the serial signals.
Yep.
And so if you have two modules plugged in, you only want to have one CS pin high, assuming they're sharing the serial clock data in and out signals, which you would often do. The CS pins will be independent, and you'll turn on just the one that you want to talk to at that point, and then turn that CS pin low or high, turn it off, and then turn the other one on and do serial communication.
Okay.
It's just a different serial protocol. The main difference is SPI allows you to go much faster.
Okay.
You can have a 10 megahertz clock frequency signal, whereas with I2C, you can only go up to about 400 hertz. So
wow. Okay.
Quite a bit slower.
Quite a bit difference, yeah.
In the particular case of this device, I2C is plenty fast enough because it only updates at maybe 100 times or something a second. It's not super fast.
Okay. And then we have int 1 and int 2. And what are those?
Right. So those are interrupt signals. And on this particular device, the int 2 is just a data ready indicator. So the modes you can put the gyroscope into are like continuously read data and just send it out on the, put it into the registers that you read for X, Y, and Z, which are your yaw, pitch, yaw, roll. That's probably how you used it, is just put it into continuous output mode and then just read the data. Correct. But you can put it into a,
like a low power, wait for this to happen.
Low power mode, or you can put it into a polling mode, they call it, where you basically read that interrupt pin, and when the interrupt pin signals that there's data ready, you go read the data, and that ends up clearing the interrupt pin, and then the thing will do another reading and fill in the registers and send the interrupt pin high again. So you can set up something where the processor can operate at a lower frequency or low power mode. And then the other interrupt pin is to allow you to programmatically set up certain things that are important. In this particular case, if you can set up a threshold value for a high rotation around one of the axes or a low rotation speed around one of the axes. So you can have it give you an interrupt if you get a high reading or a low reading in one of the axis directions.
Gotcha.
Which might be useful for different kinds of things that you would be using the thing with.
Gotcha.
Most people probably wouldn't even use the interrupt stuff. They would just set it into continuous mode and just read the values.
Right.
You know.
Okay.
Mm-hmm.
So as with all kickstarts, we have some code here down a ways, and it looks like it doesn't require a specific 3-axis gyroscope module object, just our typical full duplex serial for the Parallax serial terminal.
And then it has the I2C code just embedded right in it.
Okay.
Just like some of the other modules, this source code has the start, stop, send, and receive functions that are just doing the I2C protocol in spin directly.
Okay.
Those are the pry.
You mean like the control registers?
Well, like, you know how it has at the end, there's the pry send and private receive and start and stop. Those are being used by the other functions to send commands to the chip using I2C protocol. So those are what those control register, status register, and the out X registers, those are used along with that.
So now is this spin I2C or is it like PASM?
No, it's spin.
Oh.
It's right there at the end of the code in the Kickstart. You can see the start and stop are at the very end. And all they're doing is setting the data and clock pins off and on in a certain sequence to signal that you're starting communication.
Oh, so it's kind of like with the ping sensor, how you have to like prime it with like a low and then a high. So
basically,
it's kind of like that, where to start it, you have to.
Except that's to start the communication with I2C. It's not to start the module reading its
right.
So.
Yeah. I know there's a difference. I'm just saying it's kind of like the
kind of like that, yeah.
Like the CQ in a
saying
ham
we're
radio.
about to. Yeah, it's like it's saying we're about to start sending or receiving a bunch of bits.
Okay.
And so we're going to set these pins a certain way, and then immediately after you do that, you do one of these either send or receive, where it sends a byte or receives a byte.
Okay.
I see. To read in, and it does it one bit at a time by reading the pin one bit at a time and shifting it in.
I don't know that if I would be able to write my own code for this.
Yeah, well, it's a little bit advanced, but it's a little advanced, but I think, you're not that far away from being able to understand that spin code that's down there in that I2C code, because you've done stuff similar to this, just less of it at the same time.
Right.
It's really not that far away from setting a bunch of LEDs a certain way and then, causing them to flash. It's just doing the same thing in a particular order so that it sends the appropriate value.
Okay.
Right.
So I don't know that it would make much sense if we went through this code like line by line, because I think.
Well, we can go through the very top part where it's just talking to the module and reading out the values.
The pub go.
Let's not worry about the I2C stuff. Just focus on the module itself.
Okay.
Yeah, and I was just trying to explain.
We only got a couple minutes left, by the way.
Yeah.
Yeah. Okay, so we start the terminal. We set the modes according to whatever the modes are. I'm guessing you can find that in like a data sheet or.
Yeah, the data sheet explains how to set these control registers up, and they're basically just setting it up for the standard, enable all the axes and do the updates, and this one actually is setting it up to do the data ready signal.
Okay. And then last ticks, a local variable is made equal to the current clock cycle.
Right.
Then you send set the terminal data. It actually looks like you're sending.
Yeah. It's sending the
one.
one to reset the terminal back to the top corner of the screen, which is
Oh,
the
I see. Setting.
terminal
I see.
thing.
That's okay. Oh, I
And
see.
then
Set terminal data at top of screen. Okay,
Yeah.
gotcha. And then
And
you
then
wait
and
for
then it does a
data.
wait for data ready, which is actually going to wait for that interrupt pin, or it's actually reading the status register, which is the other way you can do it. So the interrupt pin is the hardware way of doing it, or you can read the status register in the chip to see if there's any data ready. So
Okay.
it's doing a little loop there, constantly reading the status out of the chip to see if there's data ready.
Okay.
And then once there's data ready, it comes back and reads out the X, Y, and Z data.
Okay, and then so XYZ you want to minus by CX, CY, CZ, and then divided by 114.
Yeah, so the 114 is just dividing the value, reducing the lower bits out so there's less noise. It's just the device has a really high precision.
Uh-huh.
So it's like going to, 1.000001.
Yeah.
And it's basically just saying ignore the 0.001. We only care about like 1.0 or 1.00.
Huh,
so that's essentially what the divided by 114 is doing there. And this particular demo code is doing a thing where it's keeping track of the value that it read the first time around, which is the CX, CY, and CZ.
Mm-hmm.
And then subtracting it from what it currently read and dividing to end up with, a relative rotation. But it's, like I said, it will have drift and whatnot.
Okay. And
but
then...
that's all it's doing there. Raw XYZ is just printing out the values.
Okay. And then we just wait for a little bit and then repeat that.
Right.
So when I ran this, it shows essentially in like your PST, your Parallax terminal, serial terminal, raw X equals, or raw X50, raw X whatever, raw Z. And that's when you're moving it. And when you stop moving it, it tries to stay at 0 because, again, the rate is 0 degrees, right?
Right.
So that is that. But I did want to show you guys another link. There is this cool project that someone had put together, Ratronic on the Parallax forums had put together, and he put together code and things like that where you could use your gyroscope to control an RC servo. So if you rotated your gyroscope one direction, the RC servo would go one direction, and if you did it the other direction, then the RC servo would go the other direction. And It for me personally anyway, it was neat to see it actually making something happen as opposed to just numbers.
Well, and that fits exactly with the thing we were talking about earlier, which is the servo is reacting to the gyroscope turning.
Right.
And if the servo was connected to the counterweight, right, it might cause the gyroscope to rotate back the other way, and then the servo would turn back to move the counterweight back to the middle. Right. So you can imagine it being the feedback mechanism.
And you just want to, set that feedback loop up such that it goes in the correct direction, which is less and less motion over time, right? So it's coming to its stable position.
Right.
Instead of swinging farther and farther each time.
Right.
Which you can do very easily if you get your code wrong.
Right.
Yep.
So I'll just link that so you guys can play with it, because I was like, oh, cool. There's like an application to all these numbers. But I think we're out of time.
Yep.
Yeah.
So gyroscope success.
Gyroscopic mechanizations.
Eventually, we'll probably you'll end up doing a project where you use this and an accelerometer and other stuff together, and we'll get you past your fear of filters.
No, never. Kalman filters are the devil.
It doesn't have to be a Kalman filter, but it might be some other kind of filter.
Maybe.
Well,
there
guys,
are much simpler ones.
That is all the time we have for this week. thank you everyone for listening. And you can find this show every week on Tuesday evenings at firstspin.tv. Until next week, bye.
See ya.
See ya.